All right. So radioactive decay is
Hmm.
the topic here. Um, and let's talk about it. So what can you tell me about?
Like a half-life or
Hmm.
so it's the amount of time that it takes for like half of a like half of a piece of material to like decay. So um or like yeah. So the thing is I haven't really memorized like the alpha decay, decay, but it's hard to like memorize and like kind of quickly pick up like what are some like the tips.
Okay.
I guess I was thinking that alpha decay, I noticed that okay, from cesium 137 to barium 137, like the periodic table, it looks like it gained
So let's just talk about this like
or-
at its essence, right? So now what particles are inside of a nucleus?
sure, protons and neutrons.
Okay. And protons would repel one another, right?
Hmm.
So it's kind of weird that a nucleus has a bunch of protons, right?
True.
So now I'm gonna simplify something um, by saying that there are only really four forces in the universe.
Hmm.
And the reason that this can greatly simplify things is because it's easy to get confused with what about normal force? What about force of gravity? What about frictional force? What about buoyant force and all those things? But those are all just consequences of the forces I'm going to list here. So there's gravity, which exists between masses. If
Hmm.
something has a mass, it can react to and be subject to gravity. Next one is electromagnetic. So like the electric force, which is like with Coulomb's law and stuff. Um, and magnetism is a consequence of an electrostatic force. Basically, if something with a charge exists, it can be subject to the electrostatic force. And if that charge is moving,
Hmm.
it will produce a magnetic field. Um, and this is true for charges as well as photons of light. All right. Now, these two are pretty much the only for like the forces that could be used to describe pretty much everything. So what I mean is like I think I may have mentioned something like this before, but if gravity is pulling you down into the center of the Earth, why are you not at the center of the Earth?
Because there's another opposing force, right? So like Newton's first or second law, like every, like the normal force, there's going to be another opposing force. So like the net force will equal zero, right?
So those are like so like uh normal force, force of friction, buoyant force, and all those things. Those are all just consequences of these.
Hmm.
So tell me, like, at its heart, like why it is that you are not at the center of the earth.
Because I mean, there's a greater or equal force of keeping me down, right? So like for example, like gravity is keeping me down. So
Well, so gravity is pulling you down to the center of the earth, but why are you not m moving to the center of the earth?
is this something to do with like center of mass or inertia? Or am I?
So just from what I drew right here,
Hmm.
okay? So if this is bringing you to the center of the earth,
Hmm. Then
this,
it's keeping me
uh-huh,
from going to the center.
yes. So now let's think about that, right? Your at the atoms of your body or an object
Hmm.
around the nucleus are a bunch of electrons. And if I take two atoms and I try to bring them close together, the electrons repel, right?
Correct.
So that's the real answer. So that's when I say the real answer, I mean like things with center of mass, things with normal force, things with Newton's third law, and all that other stuff are consequences of these forces, which ultimately explain pretty much everything.
Okay.
Like not like if you cannot explain something with these forces, it cannot be explained.
I guess it's so hard to wrap your head around like the electromagnetic force because of the way that it's always like portrayed in like word problems that it's, electrons or protons and you have your gravitational field and then you just kind of have to like think about it in terms of that. So I would never like think about, okay, me as like a person, like electromagnetic like force, like how is that kind of related to gravity and
So the electromagnetic force is a way for us to describe both, you know, the electric force and the magnetic force. Magnetic force is just a specific application of the electrostatic force when it comes to a moving charge. So let's just think about electrostatic force for now. So that means essentially that like charges repel and unlike opposite charges attract. So so really the gra if the electrostatic force did not exist, you would be just pulled to the center of the earth. But the reason that you are not is because the electrons of your atoms repel the electrons of the atoms of like the chair you're sitting on, which repel, etc., right? And last time I showed you like how they're pretty much look the same, like the formulas, like with this and this.
Mhm,
It's just that the constant for big G is a tiny, tiny, tiny number.
mhm.
The constant for the Coulomb's law for electrostatic force is a really, really large number. So the electrostatic force is significantly stronger. Um, yes. So now, okay. Now the other things are there's something called the strong force, which is because when we're thinking about how in a nucleus you have protons and neutrons. Neutrons don't have a charge, so we don't have to think about them, but protons have like charges. They should repel, but if they repelled, then we wouldn't have atoms. So that's something called the strong force. And the strong force operates at extremely small distances, right?
Mhm.
Um, and that is something that can supersede the electrostatic repulsion otherwise.
Is this like the intermolecular force, like those forces like between particles, like the strong force, or this is just completely different?
So, in the word, right, intermolecular
Mhm.
would mean between molecules, right? And molecule is consisting of various atoms, but we're going down to the subatomic level.
Mhm.
So, uh, so it doesn't really even so yeah, it's not going to be anything that intermolecular.
Mhm.
Um, it's within all of that. It's within the atom. It's within even the nucleus of the atom. But yes, you have a bunch of protons that are held together due to the strong force, and all of the forces exist, right? But at a very, very tiny distance from one another, you will have the strong force of that will be having a greater magnitude than the electrostatic repulsion.
Mhm.
So, and so like for instance, let's just say that these two protons are separated by a distance r, and let's say that they are at the maximum distance for which the strong force supersedes the electrostatic force. Okay. Now, let's say that we took a neutron and we just shot it here, right? It would be like, well, so yeah, so let's just say like that's the maximum distance it could be. If we shot a neutron here, it would go in between and it would force the protons to go a little bit
Hmm.
further. And when that happens, the electrostatic force supersedes and the protons repel each other. And that's how you split an atom.
Okay.
Back in like the 30s, it was like a German lab, like a lab in like Berlin, like figured that out, and that's what led to like nuclear fission and like atom bomb and stuff. Anyway,
Mhm.
that's a strong force. And then there's something called the weak force, which is just the force that's responsible for radioactive decay. And like 99.999% of anything you'll be asked will be based on these two forces. Um, Whereas the strong force, they won't really ask you anything other than what I told you, but there wouldn't really be like a formula for it or anything like that. And then the weak force, just responsible for radioactive decay. Now, if we were to graph the number of protons, so like usually the number of protons in an atom is equal to the number of neutrons,
Mhm.
usually, right? Um, so let's say that, so we could just put we could graph it as like a straight line. Now, anytime you have an imbalance, like let's say something like some atom is over here, meaning that it has a larger amount of protons than neutrons, we can call that neutron-poor. And what that will result in is, because if you think about it, a proton with like a +1 charge can decay into an electron, or rather, let's see. Oh, so a proton can decay into a neutron with the 0 charge, and a positron, which has, so I guess I'll also do this. Okay, so let's see. Okay, so a okay, an electron has a charge of -1, a mass of 0. A proton has a charge of +1, mass of 1. A neutron has a charge of 0, mass of 1. So you can kind of think about, like, let's say that you took a neutron and you took an electron and you like forced them together, or the other way around, a proton. Okay, I'll just explain it like this. So if you have too many protons and not enough neutrons, there will be some type of decay that will convert a proton into a neutron to conserve mass, but will also produce, to conserve that charge, it'll
Mhm.
produce a positive beta particle, which we can call a positron.
Okay.
And then let's say something, and so this can then decay in this way so that we can have a more stable atom. But let's say we have something here where we have more neutrons than protons, and then that could result in a neutron decaying into um, like a proton and a positron, something like that. One sec.
And the beta is what's it called? It's just called a positron, or what did you say?
Yes. So that can be considered, um, or you could think of just taking an electron
Mhm.
and making it have a positive charge.
Okay.
So just like an electron, it will have a
So zero
mass.
mass, yeah,
Yep.
positive charge. Yep.
Yeah. So, okay. So basically, um, a proton can decay into a neutron and a positron, but you could also have, if you have too many neutrons, this can decay into a proton and an electron. So, so you can see that, yes, that if you have if you don't have enough neutrons and you have too much protons, a proton can simply decay into a neutron and a positive beta particle, which is called a positron.
Hmm.
And then if you have neutron-rich, which means you have too many neutrons and you need less of it and you need more protons, a neutron can decay into a proton and an electron. Okay?
Okay.
So that's the fundamental basis for radioactive decay. Now, so now the different types will be, so this is your positron, and well, I guess this would be an example of positron decay. And then if they say beta,
Hmm.
they really just mean an electron, um, which we could say is a beta particle, kind of like a positron, but negatively charged, so -1, 0. And your beta decay is what this would be, because this would be the same thing as that.
Hmm.
So ultimately, what does this mean? It means if you are neutron poor, you will have positron emission.
Hmm.
If you are neutron rich, you'll have beta decay. And now this also means because beta particles, whether it's a positron or an electron, they don't have any mass. So that means mass is conserved. But the identity of the atom, since the identity of an atom is dependent on the number of protons it has, that identity can change. Now gamma decay, gamma is less, it's not like a straight up like particle. It's a type of light. So it could be thought of as like a photon, and it's just the highest energy type of light. Um, so I mean, I write the gamma. It's hard for me to kind of write the gamma
Hmm.
symbol. I usually write it like this. Um, but it won't have a mass because it's light, and it won't have a charge either. So that would be a gamma decay. Um, and I mean, if there's no charge and there's no mass, you can also realize that uh this actually won't happen if you have well, I should say this won't be the sole thing that happens when you have a radioactive decay process that actually changes like an atom or transforms an atom. But it can assist with them. And also, if you took a positron, like that's something that we can also call antimatter. And the reason we can call it antimatter is because if you take a positron and you take an electron and they touch,
Hmm.
it causes them something called annihilation. They both just completely disappear and get converted into gamma rays.
Okay. Because the charges cancel out and they have no mass and that's
Yep.
okay.
So I always think about positrons in like an anime I saw once, like there's like a positron rifle. And it's
Mhm.
like, and it makes sense because if you shot positrons at something, it would just completely obliterate it. Like there wouldn't be anything left of it. It would just they would cancel each other out like physically. So
Mhm.
that's gamma decay, and then alpha decay is think it's the same thing as a helium nucleus.
Yeah.
Okay, so like
Yeah,
a
like a
helium
mass of
nucleus,
4. Yeah.
yeah. Now that's distinct from helium because helium itself has those electrons, which gives it a neutral charge, right? But a helium nucleus, all nuclei are positively charged, so this would be a +2 charge, meaning an alpha particle will have a +2 charge.
So all nuclei except like the beta decay um don't have a positive charge, right? Like the
So,
right?
so all nuclei in general, because remember, a nucleus contains just protons and some neutrons. So
Mhm.
nuclei will always be positive. And so the alpha particle you could think of as a helium nucleus. So it'll have mass of helium because all the mass of an atom is in the nucleus, and a positive charge. Okay. So when it comes to a question like this, so it says cesium 137 turns into barium 137. So that 137 um number, like what does that represent?
Is this not like the atomic atomic number
So
or
what uh so well
no?
so by convention, like let's just say I wrote like A and like a number up here and a number down here. The
Mhm.
number on the bottom is your atomic sorry, your mass number. And the number on the top is your atomic number, and your atomic number is equal to the number of protons you have, and that is what gives a gives an atom its identity. So what that means is you could have like I don't know, like let's just say carbon. Um, you could have carbon of varying masses, which means that they have different numbers of neutrons, but they're all still going to be carbon. We just call them isotopes. But if you change the number, so the atomic number is 12, which sorry, 6, which means that there are 6 protons. If you change that, you will no longer have carbon. It will be a completely different element.
Yeah.
Like if
What
you
changes is
gain,
the neutrons.
what's up?
Yeah, what changes is the neutrons, right? Like the protons
Mhm.
will always be the same. Yeah.
Yeah, because if you
My bad.
change the number of protons, you change the identity.
Yeah.
Good. Um, okay, so yep, could X out.
Okay. So basically the cesium and because the number is the same, that's the atomic number, right?
Well,
Ultimately, or it's
so so the atomic number would uh change the identity of the atom, right? So cesium to barium, we are changing the identity of the atom, right? So this number isn't changing.
Mhm.
So that must mean that this number is not the atomic number, right?
Mhm.
So so that's a way for me to have you be able to reach this conclusion without just telling you. But now I'm
Mhm.
going to tell you also that generally, if they give you an element's name with a number after it, that number after it is the atomic mass of it, and that's just a way for us to denote isotopes.
Mhm.
Okay, so Since this number does not change, the mass does not change, which means we can rule out which answer choice.
One that involves the change in neutrons and protons ultimately, right? So positron emission would easily be ruled out.
So positron, um, beta or electron, gamma, alpha. So which of these have mass?
Only the alpha,
Correct. So if the mass does not change, we cannot have an alpha decay, right?
right?
So that's out. Okay. Now, since cesium is turning into barium, we are changing that atomic number, which means we are changing the protons, right? We're
Mhm.
either getting rid of a proton or we're like making a proton. Getting rid of it is this, making one is this. All right. Now, since we are doing that, that means that we can rule out the gamma decay because that wouldn't change that identity, right? So now we need to figure out if it's positron or beta. And so we want to think um, in the process of going from cesium to barium, are we gaining a proton or are we losing a proton? So yeah, so now we can open that up. All right.
Um,
Cesium to barium.
where is cesium?
Here?
Okay, yeah, so we're actually gaining because it's right next to it. So we're gaining a proton,
Correct.
and so it would be this one.
Mm-hmm. Good. So now the way that I like laid all this out is to be able to show you that, well, to connect a lot of things together, but to give you a way to answer questions without hard memorizing each of the things, but to understand like categorically. And like
Mhm.
if you can that's honestly it's like the secret to learning anything. You break things down to their axioms, things that are always true, and then you can build off that. And so that's why and then when we looked at this, we analyzed just like, is mass to any radioactive decay problem, you can just ask these
Mhm.
questions. Is mass changing? If yes, it's alpha. If no, it could be the other one. So then you ask, is the identity of the atom changing? Right? If no, gamma decay. If yes, then positron or beta. So then you see if that element is changing, like into a different element, is it gaining a proton or, losing a proton? If it's gaining one, it's going to be your beta decay. If it's losing one, it'll be your positron emission.
Mhm.
And it's all tied back to just how nature prefers there to be an equal amount of protons and neutrons. And therefore, if there is not an equal amount, it will decay in order to make that amount. So this means that understanding that means that you don't have because they could ask you a question like let's say they didn't even tell you. They're just like cesium 137 undergoes what type of decay? They could ask you that, and you can answer that um, without having to know that it's barium by seeing like, hey, is this neutron rich? Is this neutron poor? Compared to like because the values in the periodic table are a weighted average of the most abundant in nature. So like that's why for carbon we have the 12,
Mhm.
right? But you've heard of carbon 15, right?
Mhm.
And uh, which means it's an isotope, which means it has a different number of neutrons, right? So what could this what could this decay into?
So the fact that it has more neutrons, right? So protons will stay the same. So um it won't be gamma decay, and it won't be like a beta decay. Could it be like a positron emission where it's gaining like that neutron?
So, um, let's see, right? So, oh wait, hold on. Sorry, it's carbon 14. So,
Okay.
compared to carbon 12 is like what it wants to be. So, does it have so then you could ask yourself, does this have too many neutrons or does it have too few
No,
neutrons?
it has too many neutrons.
Yep.
Yeah. So
So, mhm.
could it just, so you're saying that if it wants to become carbon 12, it could undergo alpha decay and then become carbon, like the carbon 12 from
Well,
14?
so the alpha particle also has this charge of +2, right? So if the identity of the atom does not change, right,
Hmm.
then that, won't be it. But you can just kind of think like, okay, we want to go from here to here, right? So, and the problem is that there's too many neutrons, right? So then
Right.
it'll undergo a beta decay, right? But the only thing I guess I should have said is that you will change that identity. Um so this is actually just going to turn into nitrogen, and that's like how carbon dating works. But yeah, all in all, just think about it as yeah, neutron rich or neutron poor.
Okay, wait, let's do another example. Let me see if I can wrap my head around it.
Mm-hmm.
Um, yeah, could you think of something else that where I can be like, okay, this one is most likely it.
Um, well, okay, we could well, oh, you said a different
Like, yeah, like of the emissions and decay.
let's see. We could do okay. So, okay. Uranium 235 can turn into something plus, I guess this would be kind of similar to this, like where they
Okay.
give you like what it turns into, and then you essentially balance the sides. So this is going to turn into thorium, and I'll give you oops, yeah, this.
Okay. So I can see that the mass is changing.
Yep.
And I can also see the atomic number is changing. And so off the bat can't be gamma decay.
Mm-hmm.
Let's see. And it looks like it's decreasing, right? So it's losing its mass and it's losing its protons.
Okay.
So it can't be the one with the electron that's being produced, which I believe it's the was it the positron emission is the one that let me double check. Um or the beta, it can't be the beta decay one. So I'm assuming it would have to be like the positron emission for this one.
So the first thing we can ask is um is the mass changing?
Yes.
And then there's only one decay process that or particle that has a mass.
So it would be the alpha decay.
Yep. And so now what we can do is we can write, oops, we can see if, so here, I'll write that. And so now we could just see like, all right, is this conserved? Meaning like the numbers on the left equal the numbers on the right.
Mhm.
So the, I think I keep messing up where I write the
The mass number and the
mass.
atomic number, me
uh,
too. The mass number
Oh,
is always
yeah, yeah.
on the top, right? And then the atomic number is on the bottom.
Correct. Um, so yeah, so okay, so on the so if we add up the mass numbers on the right, we get 231 plus 4, which gives us
235.
235. And then if we add the atomic numbers on the bottom, we get 90 plus 2, which gives us 92.
Mhm.
So that's how you would be able to answer like a question like this or something like that by writing out something like this.
Mhm. Okay. I just have to remember that positron emission, like there's again not going to be any change in like its actual like weight. Like the weight will always stay the same. It's all about like the charge.
Yeah, but that'll be for everything except so you could just think about it like this. If mass changes, it will involve an alpha particle. So so you're not going to have any of the other ones because gamma doesn't have mass, positron doesn't have mass, beta, aka electron doesn't have mass.
Mhm.
Hmm.
Okay.
Good.
Right, let's see. This one was fine.
Hmm.
This one was fine. This one I realized I didn't know what the oxide meant. I thought it was O minus one, but it's O2 minus, so that's oxide.
Well, so go to that periodic table. So everything wants to be have like a completed octet.
Mhm.
So for any given element, you can just see, so like for instance, let's just say beryllium, right? So in order for it to complete its octet or whatever, it could either gain one, two, three, four, five, six electrons, or it could lose one, two.
Right.
What would be easier?
To lose it.
So that's why it'll turn into a 2 plus cation, right?
Mhm.
All right. Now, carbon could gain one, two, three, four, or lose one, two, three, four. I guess that's kind of like
That's why it's plus
a little bit.
minus four on like
Oh,
the
okay, okay. Yeah. So, yes, carbon would want to do that. So then with oxygen, one, two. So it would want to lose two electrons,
Mhm.
right? So, um, so yeah, that's like a quick way to if you don't remember if it's like one minus or O2 minus or whatever, you can always just see how far it is from the nearest nearest noble gas. And also when it comes to the word, um like if it ends in so okay, if it ends in like ium, it'll be like a cation, so like sodium, beryllium, lithium, right?
Mhm.
If it ends in ide, like IDE, it'll be an anion, which is a negatively charged ion. So like oxide, halide, bromide, iodide, all of that stuff. And
Okay.
so like if they just said oxide, you would still be able to understand that this is an ion, but they are also saying ion, so we want to be aware of that. And then, oh, and how are you with like writing electron configurations out?
Uh, I think I'm okay. Like I know how to read off the periodic table. I think ultimately I was just like, oh yeah, it's oxide, so it should be. I don't know. I thought it was like because of the polyatomic ions, they always trip me up. So like chlorate or like chlorus or like the 8s, like which one is gaining and like which one's like +2 or like -1, -2.
Oh yeah,
But
yeah. Don't worry about that. Like, yeah, there's like some polyatomic ions that like I guess expected to know, but that's like something that you can like kind of like figure out. But I just want to make sure that um for instance, because you chose because I would have expected you to choose
something else.
either either like oxygen normal. So for instance, why don't you tell me the configuration of nitrogen?
So it would be 1s2, 2s2, 2p3. Or you could just write it in like the brackets of helium and
Yeah,
then
perfect, perfect, perfect. Got it, got it. So, okay, okay. So, um, oh yeah, so it'll be like, um,
so I thought I was gonna do like fluoride. So I don't because it was -1. So I was okay. My then I was like, okay, so 1s2.
I
Um
see, I see, I see.
yeah.
Got it. That's why you chose that one. Okay, okay. So yeah, you could just think like instead of like going through your mind and having to remember if it's -1 or -2, just you can look at the periodic table and see, okay, it's going to want to be a noble gas, so it's going to want to lose two. And then you just take your regular electron configuration and you remove two electrons.
Okay. Um the other thing was that like how much of like the graphical, like I've seen like a couple of like UWorld flashcards where it's like, okay, so like, the s orbital wants to be like that overlapping is kind of like this shape and then versus like the p orbital or like the pi. I guess it's like the bonds and like where the pi bonds want to sit. Like the pi bonds want to sit like at the edges of like, the p orbital. Like how um
So
like how does that
your so your s orbital is going to be your spherical shaped one,
work?
and your p orbital will be the dumbbell shaped ones, and there's three dimensions. So there's a px, you
Py,
know,
pz.
py, oops, pz. So
Hmm.
these are just the orbitals that exist in an any given atom. Now, for bonding to occur, like let's say we have two carbons here, um, put like a hydrogen here. So let's say we have um oh, what- I'll do the hydrogen after, but so let's say that we have um the like px orbital overlap.
Hmm.
And if that overlap is between the two atoms for that bond, this is called a sigma bond.
Hmm.
And I'll use a different color. And then let's say we have our py orbitals. Now, they're not in between the carbon atoms, right? But there could still be some overlap, like up here and here.
Hmm.
Maybe I'll do like a dotted line. And when you have that, that's going to be a pi bond,
Okay.
right? And then you can have your PZ overlap, which will just be another pi bond. So ultimately, your sigma bond, if it's solely a sigma bond, that'll be a single bond. And then a sigma plus pi will be a double bond. And a sigma plus 2 pi will be a triple bond.
Mhm.
And then oh yeah, and then for hydrogen, like which only has that s orbital, like
Mhm.
it'll overlap with that as well, and that would also be a sigma.
Mhm.
But yeah, that's so this is when so these orbitals exist for any given atom, and if you want to create a bond between any given atom, um, you will need the orbitals to overlap, and that also causes something called hybridization, which can then be related to like because you're mixing like the S and the P, so you can get like SP, SP2, SP3. It'll actually be like SP3, SP2, and SP, something like that. So that would be like with hybridization. Oh, and then the last thing would be because you can have your what is it called? Bonding and anti-bonding
Mhm.
orbitals. So um so like something here would be like a bonding molecular orbital. And like this part, like if there's no hydrogen there or whatever, could be the like an anti-bonding orbital. And like if something comes in and forms a bonding orbital with the anti-bonding orbital, then this part becomes bonding. And you can't just have like there must always exist bonding and anti-bonding. It's just a question of where is that shared electron going to be located. So in this bonding molecular orbital, the electron exists there. But if you brought in a separate molecule that makes it so the electron is in this anti-bonding orbital, this anti-bonding orbital becomes the new bond, and like the previous one becomes anti-bonding. But
Okay.
that, that's
I have to wrap my
we'll
head around
get
that one.
yeah, we'll get to that at some point, like way later. Like they generally won't ask that. But yeah, for the most part, yes, this
Okay.
would be, yeah.
Mm. Okay. Largest atomic radius.
So now be careful there, because
Oh,
it's
ionic.
asking about ionic radius, right? Now, if you think about it, right, just for a regular neutral atom, like your proton in the nucleus, electron, you know, out
Okay.
there, and like the distance between that proton and electron is the atomic radius.
Mhm.
And it's like the proton is like pulling that electron towards itself as much as it can. Now, if we did not change the number of protons, but let's say we added another electron, that single proton that was using all of its might to pull an electron towards itself to get a
Mhm.
certain distance between it and the electron, it now has to pull two
At the same.
electrons.
Yeah.
And and since it has to now pull two, it won't be able to pull them in as closely, right? So
Right.
whereas, let's say from two to one, like let's say its atomic radius involved two electrons that it pulled in, and you get rid of one, it can then concentrate its like pull on that single electron and therefore be able to pull it in even closer.
Hmm.
So that means that compared to a neutral atom, uh, atomic radius, a cation, which means an electron leaves, will let that nucleus pull that electron in closer. So a cation is always going to be smaller than the neutral atom.
Repeat that again. So why would it be smaller? Because it's losing like the electrons, so there's less pull.
So, so yeah, so let's say that a certain, so let's just say that we have an atom with two electrons,
Mm.
and the radius is because the proton is pulling the two electrons, like as much as it can.
It's
And then
small.
let's just say we get rid of one.
Yeah.
It would be able to focus its energy on pulling that single electron now, which means it could pull it in closer.
Hmm.
So if it can pull it in closer, the radius, the size gets smaller. So for any given atom, the cation form of it will be smaller. And then the opposite for the anion, because you're giving it more electrons,
Great.
which means it has to divide its like pull. So your anion is always going to be larger than the atomic radius.
Is this you're like, are you trying to explain what the Z effective charge? Like, is this similar or this is different?
Yeah, this is basically the measure of that pull. And when you add electrons to reduce the Zeph, we can also call that shielding.
You'll call it shielding when what happens?
So like if you if you add another electron,
Hmm.
that new electron can participate in shielding. You can kind of think of it as you're shielding the electron from getting pulled in by the proton in the nucleus.
Okay.
So we could even do a proportionality, and this is something that like just thinking in terms of proportionalities is going to be like the best way to like do any of this stuff. So meaning that we can see if a relationship is directly proportional or inversely proportional. And so like this symbol is proportional. And if something is just like A is proportional to B, like that.
Yep.
But the thing is, an inverse proportion is like this. Now, sometimes I see people do something like if A goes up, B goes down. Don't do it that way because this doesn't give us any insight as to the mathematic relationship, which would enable us to graph it.
Okay.
Because they like to ask, for instance, this inverse proportion, you would think that it would just look like this, but if you actually like plugged in the numbers, you would see that, and oh, and then also since the denominator cannot be zero, this really looks like that.
Okay.
So that's something that they like to ask. So, but yeah, bringing it back to this, the more shielding you have, the less pull Zeph you'll get. So shielding will be inversely proportional to Zeph.
Okay.
And then I could also say Zeph is inversely proportional to like, or rather, no, it's directly proportional to that radius. Oh, no, sorry, inversely proportional to the radius. If you have a larger Zeph, you have a smaller radius.
Yes, correct. Yeah.
Hmm.
So I think for this one, what was it like? I kind of like wrote on the side. I was okay, n minus 3 right? You have neon, O minus two. You'd also, so I was just kind of thinking about it like that basic like picture you probably saw like with all the trends. I was okay if you increase it this way, right? I guess I forgot the trend, but I knew that as you go down to cesium, that's where like that's the largest one. So I was like, okay, which one is like different? And then I was saying, okay, like sodium, right? Plus will also give neon, and then the only one that's left is magnesium plus two. And so that also gives, I don't know why I wrote silicon, but it would also give neon. So ultimately, yeah, that
Well,
strategy
so
was
so you got the trends right. But just to like say it again,
hmm
I draw it as a diagonal because you don't have to think about up and right if you just think about the diagonal, which is up and right, right? So this here is pretty much all of the atomic trends, but you could really just think about them as so when I say all of them, I mean ionization energy, I mean electronegativity, I mean electron affinity. You can encapsulate those all by thinking about them as how strongly they take or want electrons.
hmm
And it kind of makes sense because let's say you're fluorine, right? It's like if you are boron, it's like, hey, maybe one day I'll get to be a noble gas, but I'm not, holding my breath, you know?
hmm
Um, but as you get closer, you get more greedy. So like oxygen is close. Fluorine is the closest. So fluorine is like gonna be ruthless to get that electron to be like neon. So that's why
hmm
this pattern you can just think of as just how strongly something wants and takes electrons. And then the opposite, this one is just one trend, and that's atomic radius.
Okay.
So so yeah,
Which one?
so that would be just atomic radius. Now you also did like the electron configurations, and you found that they all gave you the same electron configuration.
Mhm.
So I mean that's still a right thing that you did. But yeah, ultimately this just means that or we just need to understand that we're being asked about ionic radius, and when it comes to ionic radius, your anion will be larger than the neutral, and then the neutral will be larger than the cation. So cations will, yeah, so like this one will be smaller,
Mhm.
right? It'll actually go like in this direction from largest to smallest.
Yeah, with the assumption that, yeah, because nitrogen, right, it has those three electrons, so the Z effective charge is going to be fairly large, and that would be inversely related to like the
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 other way
shield.
around, so think about it like this. So if this is gaining electrons, we get more shielding.
Mhm.
And if we have more shielding, you have less Zeph.
Yeah.
Because that's what, like, if you think about it, it's like, okay, why is it called shielding? What are we shielding from? We're shielding from the Zeph.
Okay.
Hmm.
This one, I think that was just like I wasn't sure what insoluble salts was, but I knew what like the definition is. I know these are alkali
Oh, wait,
metal.
didn't we talk about that last time with solubility?
Yes, but I don't think I remembered it until
Oh, so
maybe.
so uh don't think about remembering, just think about the word, right? Insoluble means that, if you took it and you put it in water, it's not gonna dissolve. So it's gonna be like a precipitate or something, right?
Hmm.
So so yeah, if if you not like don't think like, okay, I don't remember this. Think I can try to like figure it out from the words, right?
Hmm.
Um, but ultimately this question is kind of like a content thing. Um, and I would just say like after the session or whatever, just look up maybe a video of type in sodium dropped in water and you'll see some cool stuff.
Okay.
It'll basically like explode, but yeah, this
Okay.
is mostly like a yeah, content thing.
So, I guess I was thinking, I was like, okay, well, like I know sodium is a salt and it's, you know, compared, I mean, like sodium is a metal, but then compared with like chloride, right, which is a non-metal, if that's table salt. So that would be soluble in a sense, right? Because you're mixing it in water and but I guess I'll look at the video and see.
So um so yeah, that's basically right. But to connect it to what we talked about last time, there
Mhm.
will exist some maximum amount of sodium chloride that can be dissolved, and that's your like KSP, right?
Mhm.
So at some point, you can take like a glass of water and like a big thing of salt and just keep pouring it in. It'll dissolve until it won't.
Okay.
Think you could think of that way. So yeah, another like good way to think is like like if you want to like be able to understand something really well is to kind of like think in terms of like extremes or limits, right? Because yeah, you're absolutely correct. This is like the very definition of dissolving. I mean, I would even make the distinction that it's technically dissociating
Okay.
because dissolving is kind of like colloquialism. Because you could dissolve, and I'll give you like a like an example. Um, Sugar can be dissolved in water, but the sugar molecule doesn't change.
Hmm.
But sodium chloride dissociates in water, which means it actually breaks apart into those ions. So, yeah. But
Okay.
oh yeah, so yes, this is a perfect example of something that dissociates in water, therefore is soluble. But if you think about taking it to the extreme, so like I'm just imagining like just imagine you just have like a pounds and pounds of salt and you put it all in like a cup of water at
Right.
some point, and that point is the KSP. So if your concentration exceeds the KSP, it's not gonna it's gonna it's gonna not be soluble anymore. It'll be insoluble.
Okay. Then why would like so A, for example, hydroxide, I know it's OH minus. So the metals in group 1A react with water to form hydroxide. So if we have like the example of, I don't know, like sodium chloride plus water, what would, that if it's going to be dissociated, right? What would it produce? So um one is going to accept, right, the like the water is going to donate one of its hydrogen ions um, with the chloride, for example, and then it will like sodium will accept the two well, like the oxygens, right? So that would create like NaOH. Like I don't see how it's creating like hydroxides.
Got it. So let's say we just take like straight up like solid sodium,
Hmm.
which like it's not something that's like easily accessible because, well, I'll just say this first. So, okay, and then we throw it in some water and we can get our sodium hydroxide. So like that's something that's familiar, right? And same thing with the other things in the group, like potassium hydroxide. You don't see it as much, but like there could also be like lithium hydroxide. Um, plus something else. Um, what could it be if you wanted to like um balance it?
So this would be like the hydronium ion, right? Like you would have like H plus or H30, H30 or H30
Well,
plus.
H3O plus would be, yeah, it would be hydronium, but that would be like if you had an acid.
Hmm.
Um, but what could be something that you get here? I'll just put like just to make it balanced, that could help. But think about what this other thing could be. I'm gonna use the bathroom real quick, but yeah, you can think about that as they go. One sec. Okay.
So just like looking at the balance equation, like you would be creating like two more hydrogens, right? Because there's four in
Yep.
the
Very good. Have you ever heard about the Hindenburg crash?
no.
So like uh also maybe afterward, like YouTube it, because they actually
Okay.
have it on film, but they used to so you know what like a blimp is, right?
No, I live under a rock. I don't know.
It's like a flying big, kind of looks like a balloon almost. Kind of looks like something like this. I don't know, kind of like that.
Hmm.
So anyway, um, the Hindenburg, so blimps today use helium. Um, it's less dense than air, so it floats, um, like a balloon. But hydrogen, H2 gas, is also, uh, even less dense, so it floats. So back in the day, like, they initially would make a blimp kind of thing with hydrogen gas, and a great example is the Hindenburg. But the thing with hydrogen gas is that it's highly flammable.
Hmm.
So something happened and it kind of like burned down and all this stuff that you'll see in like a video. Um but yeah, you're making hydrogen gas, and that's why when you like YouTube sodium dropped in water, you'll see that it'll make an explosion, and that explosion comes from that hydrogen gas, H2 gas.
Okay.
You also make it in to connect it to electrolysis when you use electrolysis to separate um uh to electrolyze water, split it into oxygen so that you can breathe if you're like in a submarine.
Hmm.
But you also make that H2 gas, so you need a way to deal with that unless you want like the submarine to like blow up.
Sure.
But, but yeah, just always try to make as many connections as possible. Um, because that way you just don't have to remember as many separate things, you know?
Okay.
Cool.
What are hydrides?
So, what can you tell me based
Okay.
on? Yep.
Hydrides. Is it like minus
Yep.
something to do with like the minus sign?
Yep. Yep. Yep.
So oxide is -2, then would hydride also be -2?
So yeah, it'll be a negatively charged hydrogen, basically. Um, and then the opposite, remember what suffix I said would be for like a positively charged thing?
Would it be EM?
Yep. So hydronium, right?
Mm-hmm.
And they're hydroxides. But
Okay.
yeah, hydride is going to be a negatively charged hydrogen. Nitride, negatively charged nitrogen.
Okay. And then ox hydroxide, negatively charged oxygen, right? Or
Well,
like OH.
oxide would be the negatively charged oxygen, but the hydro means there must be a hydrogen involved. So that's the OH minus.
Okay.
Mhm.
Mm, This one, I didn't know what second ionization energy meant. Um,
Okay. What's just regular ionization energy?
s- Something to do with valence electrons. No?
So so there's probably nothing that doesn't have to do with valence electrons. But um let's think about like anything, like you're gonna hear me say this like all the time. Like let's look into the word
Okay.
itself. So what words are inside of it?
Right. Like it's ionization energy. It's like the amount of energy it takes to ionize.
Yeah, there you go. Good. Good, good, good. So now this is also that trend of that, meaning and that should make sense, right? Because remember how we said that this trend is a measure of how much something wants an electron.
Mhm.
So if something wants an electron really badly, it's not gonna want to give away electrons it already has. So that's why this periodic trend is also that of ionization energy, right? So now, if first ionization energy is the energy it takes to ionize something, and I guess when we say ionize, we could mean like stripping away electrons, taking away electrons.
Mhm.
Then after the first ionization, the second ionization energy is the energy to take that second electron out, right? So now, so yeah, so now let's look at the periodic table for this.
So I can see what I guess for magnesium, for example, I know that it has like a plus charge of 2. So, it would much rather like lose 2 electrons to become stable. Um, so wouldn't that mean like it could easily give away like the first ionization energy, like that would be higher, but the second one would be a little bit lower, which is why D is incorrect. But
So let's see, right? So if we remove one electron, we'll be like, we'll have the same electron configuration as sodium, right?
no.
And that's not enough, right? It can do better, right?
Mhm.
So let's remove a second one to be like neon, right? And
Mhm.
it wants to do that, right? So if it wants to do that, it's gonna have a low ionization energy and second ionization energy, right?
Okay, so it essentially is like the amount of energy, like it needs um less energy to like strip away its electron
Yep.
versus something like fluorine would have a very high like ionization energy to strip away all of its, you
So we
know.
could think about just if something wants to do something naturally or spontaneously, it won't require that much energy. If it doesn't want to do it, it will require like that much energy. So this magnesium will have a small first ionization energy and a small second ionization energy, but once it's neon, it doesn't want to do anything else. So it
Mhm.
would actually have a really high third ionization energy, right?
Mhm.
So like it's not like you have to think about what's the third, what's the fourth, what's the fifth. It's just to show you that it all can be brought back to what we talked about earlier, which is things want that octet filled. So does it make sense that magnesium would have a really high third ionization energy?
Yeah, because it's going to be most stable there, so it won't want to do anything.
Exactly. So now let's try sodium. So
Okay.
sodium first ionization energy is going to be small, so it can be like neon.
And then second would be very high because it won't want to
Yep.
lose any other electrons.
Yep.
Um, then okay, then let's talk about like beryllium. It's the same thing. So it's a low first ionization energy and then a very like high second ionization energy.
Good question. So now we combine it with our knowledge of ionization energy and that periodic trend,
Hmm.
right? So if this is higher ionization energy, let's see. So lithium compared to sodium, it's not to the right of it, so don't worry about that, but it is above it. And if it's
Yep.
above it, it has a higher first ionization energy to begin with, right?
Hmm.
So when it becomes helium, its second ionization energy is going to be high, and it's going to be even higher than that of the sodium because it starts off higher.
Okay.
This is using both. Like you can tell how like these types of questions um like exploit the straightforward type of questions that you're used to, where it would be like you just look at the periodic table. So the MCAT knows that you know it, and so it will rarely be that straightforward. So we had to think about both of those. Think about just the periodic trend as well as, you know, figuring out second ionization energy based on what it, turns into.
But then why is lithium the correct answer? Because great again, it's greatest second ionization energy. So first ionization energy to move to helium, okay, low. But then second ionization energy to move to hydrogen would be high. How?
Well, so when it's helium, it wants to be helium and it doesn't want to change, right? So lithium's going to have a high second ionization energy, right?
Well, I guess my question is like, why is the answer like not beryllium? Because if you this is, low first and then high second, this is low first, then where does the second one come to if ultimately we're talking about?
So one ionization to get it to there,
Hmm.
second to get it there,
Yep,
where it wants to be.
sure.
So it wants to be ionized twice, which means it'll have a small second ionization energy because it wants that second ionization, right? So it
Okay.
would have a high third ionization energy, just
I,
like magnesium would have a small second ionization energy and a high third.
mhm. Yeah, I just need a minute to wrap my head around it. Yeah, but that makes sense.
Mhm.
Um,
Ah, stoichiometry with dimensional analysis. So dimensional analysis, most important skill you can have.
mhm.
And okay, so ha
How
tell
did
me
I
about
approach it? So I think first what I did was I like calculated. So I knew I was given 2.25 moles of nitrogen gas, and it's asking how many grams of sodium azide must be stored. So I have, so in some like that is like the amount like the dimension I'm giving. I'm given 2.25 moles of basically of like each mole of nitrogen gas, and there's 3 moles of nitrogen gas being made. So I think I went ahead and tried to.
So before we do anything, let's look at the big picture, right? So we're given this balanced reaction here, and that shows us this, mole ratio, meaning like, yeah, if you had 2 moles of whatever, Na and sodium azide, you'll get 3 moles of nitrogen gas, etc., right? So that's what that's telling us. Now, they're asking us for grams, right?
Mhm.
So what enables us to connect moles to grams?
Like the atomic mass units, right? Of a certain.
So the molar mass, right?
Mhm.
AKA the mass in grams of a mole of something. And that's your conversion factor, right? So here we are okay, so they're saying here that okay, 2.25 moles of this nitrogen gas is needed, and we need to figure out, well, okay, we use the moles of nitrogen gas along with the balanced reaction coefficients
Mhm.
to first figure out how many moles of sodium azide you get,
Mhm.
and then we'll use the molar mass to convert the moles of sodium azide that we got into grams, into mass. Okay?
Yep.
So, like, so big picture view would be like moles of this, use like the balanced reaction to figure out moles. Oh, it's the other way around. So moles of nitrogen gas, and we use the balanced reaction to figure out the moles of sodium azide.
Mhm.
Then we use the molar mass of sodium azide to figure out the grams of sodium azide.
Yep.
That's the big picture way of looking at it. Um, and then we can like do the math and all that.
That's what I started up doing. I did 2.25 2.25 moles of N2 gas times 2 moles of sodium solid over 3 moles of nitrogen gas. And then for some reason I multiplied it by 23 grams. I guess I was trying to figure out like the mass of sodium per 1 mole of sodium.
So
But
what you wrote down, I want to know if you just wrote the numbers or did you write like the
no,
units?
no, I put the units down.
Okay. So, uh, okay, so sorry, tell me again what you did.
So I did like 2.25 moles of N2 gas times 2 moles of sodium, like solid, over 3 moles. This is like the
Mm-hmm.
yeah, moles of N2 gas. And then I think where I messed up was I don't know where I got 23 from. Maybe I was trying to find like the sodium, but 23 grams I said of sodium over 1 mole of sodium. So obviously that was incorrect. It should have been like once I was on that second step of the moles of NaN3 was to use that, right?
So I think what you did was you just used the mass of sodium.
Yeah.
So, yeah, so you would just use the mass of this.
Yeah, so I would have to calculate the nitrogen as well in there.
Mm-hmm. Should
Um,
be 45. Well, yeah, 45.
yeah,
So 68. But if you set it up properly, then you're good.
see, so you
Hmm.
were getting 65, right, for the total mass?
Yep.
Yeah. So it should have been 65. And I don't know why I didn't use it in the dimensional analysis, but yeah, 65 grams, right, over 1 mole of NaN3.
Hmm.
And then wouldn't you also have to like multiply it by like 2 though? Because there's 2 moles of NaN3.
Okay, here, let me see. So I'll set it up. So 2.25 moles N2, and then for 3 moles of N2, and this is like how you're doing it, right? With
Is
good.
exactly how I did it. Yep.
All right. 3 moles of N2 gets you um 2 moles of NaN3, and then 1 mole NaN3 will get you, what was it? 65
Yep.
grams
65 grams per mole.
of NaN3, and then all these things cancel will give you your grams of NaN3. So now I can tell
You know
you
what?
how, yeah.
I know exactly. It's the same thing that I did wrong, like even last week. So right where you wrote the 2 moles of NaN3, I wrote 2 moles of Na solid.
So maybe when you saw sodium azide, you didn't know what that was and
Hmm.
you thought it was sodium, or maybe you missed that part.
Yeah, I think I was like adding an additional step where I was like, I have to use like the molar ratio of the products before going to like the reactant side.
Hmm.
But I now I know that you can just kind of you don't have to put that to sodium, like 2 moles of sodium when you know like it's 2 moles of sodium azide that's creating these two products.
Well, yeah, yeah. So the sodium, we don't do anything with it.
Mhm.
Um, but they could have asked us, you know, how many grams of sodium, and it would actually be similar to, I mean, it'll be the same number of moles as sodium azide. So your answer was probably the correct answer for the grams of sodium used.
Sure, I'll try doing it again.
Hmm. So I think it was just like a mix up because sodium is also here.
Mhm.
Either that or maybe you thought you had to use it.
Yeah, I think I was just like I thought I had to use it.
Hmm.
But yeah, no, I mean it makes sense now.
So when it comes to like this math, like without a calculator, like d how do you like feel about
I
that?
mean, it took me like 4 minutes, so
Oh, okay, okay. So I can show you some like tricks of like how I would do it.
okay. Is it something like you're rounding up or down? So like for 2.25, you'd be like, okay, let me round down to 2. And then, you're like cross multiplying. So 2 times 2 is 4, then 4 times 65. And you could be like, oh, well,
So
what is,
I just would, well, for the most part I use fractions because
okay,
that means that, well, two things. It means that you don't even need to round, and then two things cancel out. But I'm going to do a combination here, so I'm just going to do this. I'm going to do 66. 3 goes into 66. 22 times 22 times 20 times 2 is 44. And I'm really just going to do like 40 times 2, which is like around 80. So I'm going to
mhm,
get 80 as a lower bound, right? And then I'll do the upper bound, like just doing like 40 times 3 or something like that to
okay,
get like an upper bound of like maybe 20, and then I would go in between like that. Uh,
okay,
Alternatively, what I would actually really do is the 2.25 to 2 1/4, and
mhm,
I can turn this into an improper fraction, which is 9/4. So then it'll be 9/4 times 2 thirds.
mhm,
This goes into this twice. This goes into this 3 times, right? Times the 66. This goes into this. The 33 times, 3 times 33 will give me that.
mhm.
So, I mean, that'll take some practice, um, but yeah, we can always talk about that. But yeah, I know that a lot of people say like round something up, round something down to equal it out, but that can be misleading because if something's in the denominator and you make it larger, it overall becomes smaller and all of that stuff. So so yeah, I would use fractions. I think that's it's like if someone calculates, how would you calculate like a 20% tip, like if you were at a restaurant or something?
Oh, when I was in middle school, there was like this formula, like is a of equals number of a percent. So I would ask myself, okay, what is 20% of, like, I don't know, like
So I
20.
would just, so 20%, 0.2 is 1/5. So I would divide it by 5.
Okay.
So that's something in the shared drive PDFs folder. I have a couple of PDFs called math and
Mhm.
math tricks and stuff. But I basically just like use these, yeah, like I like kind of like memorize like the different like 1/7, 1/8, 1/9, all of that stuff, and it really gave me like an edge when it comes to like the MCAT math and all that stuff. And
Mhm.
you could then also find like patterns, like this, like the R, the ideal gas constant, is really just that.
1/12. Okay.
And the one of the coolest things, this isn't even related, but let's say, you know, the formula of like a cone or something like that could be something like this. Whoops. But, and it's like, I don't know why no one else like noticed this, but like pi is basically 3, so it's really just that. So like this really just tells you that any volume is in 3 dimensions, so it'll just be proportional to like a side cube. But anyway,
Mm, okay. Let's see, I got 11 right.
yep. So this is just like the same exact thing, just in a different order. So it's good that you could do this stuff. Because sometimes like if I have like a student that has trouble with this, it's like, oh man, we need to do a lot of work.
No, no, that's coming too towards the end when the Orgo stuff comes. Don't worry. Let's see. This one is fine. This one was fine.
So like eight versus ite and ick versus us.
So us is so it's kind of like a like step up. Like one is greater than the other, one is, less than the other one. I think eight is like -1, and then like us is -2, and then ick is -3 or
So that could be like um that can depend, but thinking in terms of strong and strong is the right way. But so okay, so if we have like an acid that
Mhm.
ends in ick and it loses it, it's done its job of losing a proton, it'll turn into eight.
Okay.
And that, by the way, could also be called a salt. Like so yeah, like sulfuric acid can turn into sulfate.
Okay.
And then the weaker one will be OUS, like sulfurous acid. And the salt of it, when it gives away its proton, will be ite.
Okay.
Okay, now let's go even beyond this. And what's a word you would use to describe, like, let's say, a little kid who has a lot of energy?
Hyper.
Yep. So per,
Mhm.
and what could you say, like, if you have too little of something?
Um, Negative. I don't know.
Yeah, that was too vague of a question, but you said you're like a PA or something?
Mhm. Yeah.
Okay, so what would be, let's say someone like the diagnosis of someone who has too little of something, maybe?
Okay. Like hypo. Yeah.
Yep. So like you could have chloric acid, chlorous acid.
Hmm.
Oh, and then by the way, like for oxy acids, the strength of that acid is proportional to the number of oxygens. So that's why like SO4 would be like sulfate, sulfite would be like SO3. So so yeah, you're um like HClO4 is perchloric acid, O3 is chloric acid, O2 is chlorous acid, and O just regular would be hypochlorous acid.
Okay.
So, yep.
So this has nothing to do, look, with like a negative charge. It's just about like the amount of oxygen ultimately.
Oh, um so like these are would be describing the acid form, which is before it gives away its proton, so neutral.
Okay.
And once it gives its proton away and becomes negatively charged, it'll be these types of things.
Okay.
So for instance, H2SO4 versus um, this, or
Hmm.
rather, let's say after it loses both protons, it'll be this. So on the left is sulfuric acid, on the right is the sulfate ion.
Okay.
So here they're just so all the examples here, like I mean they give us extra information with ion, but they don't have to, but if it ends in ATE, it's going to be an ion. If it ends in ITE, it'll be an ion. If it ends in IDE, it'll be an ion. Uh,
What's why do you keep saying that ion is a huge hint? Like
oh,
I
because like, well, if someone just gave you oxalate,
uh-huh.
you should know from it having a suffix of ATE, just like if it had a suffix of this or this.
Right.
I said the same thing with that question that said an oxide ion.
Mm-hmm.
I was like, yeah, the ion is like a big hint or whatever. Like, what I'm trying to say is you should be able to not need that word.
Okay.
So, so if they just gave you oxalate without the word ion,
Hmm.
you should also know that it's an ion. Yeah.
Yeah. Okay.
Hmm.
And then if it like lost only one electron, H2 SO4 minus one, or yeah, or H1 HSO SO4 minus one, that would be uh IH, right? Like
Oh, sorry. So the I is going to be if you had SO3.
okay. So it's losing one oxygen and so
Sorry.
like what would
So,
the equation look like, I guess?
okay. You would lose. Okay. So let's see. Okay. So we have sulfuric acid
Hmm.
and, well, I guess, okay. So let's say it just loses one first. I guess I didn't mention that there could be like for polyprotic
Hmm.
acids, like eh, okay, so -1, like this would just be hydrogen sulfate, and oh, and then I'll just do this because it's losing its proton as an acid, and then this, so now this is going to be sulfate. Okay.
Okay.
Now, if I just did the same exact thing, I'm going to use green. So if this was a 3 in all of these,
Hmm.
then this is sulfurous acid.
Yes.
What would this be?
This one right here,
Hmm.
wouldn't this be like sulfuric acid then?
Well, um, okay, so the ick
Hmm.
is going to refer to, we'll always have more oxygens than us,
Right.
just like per will have more than ick,
Hmm.
right? So in like this overall reaction, there's no change in the number of oxygens because if that was the case, it would be a redox reaction.
Hmm.
Instead, we just have an acid doing what acids do, which is get donate protons. So really, I'll just go back to H2SO4 is sulfuric acid, and when it loses its first proton,
Hmm.
you get hydrogen sulfate
Okay.
ATE because this is
It's
with this over here. Yep. And then it could lose another proton to just be regular sulfate.
hmm.
And then I use orange. So now same exact thing, but instead of four, if we had three oxygens in all of these cases, then it'll just be sulfurous acid. And then this would be hydrogen sulfite.
Hmm.
And then this would be sulfite.
Okay.
Hmm.
Yeah. All right.
And then I'll just say one more thing to have a broader category would be if this is our acid, this is our conjugate base.
Hmm.
Okay. Now, for polyprotic acids, like this is a diprotic acid, what can actually happen is, I'm running out of colors, but the conjugate base, like this conjugate base,
Hmm.
could still act as an acid to produce this second conjugate base.
Right.
So that's the weird thing with the polyprotic stuff.
I think I vaguely like remember reading this, but it's just a little bit harder for them to do it the second time around, right? Versus this first conversion.
Yep, yep. Because if you think about it, this relative to this is a conjugate base,
Mhm.
whereas this relative to this is an acid. So, so this means that this is more acidic than this, which is more acidic than that.
Mhm.
Mhm.
Okay. So in summary, right, eight, I like this is all in terms of like the, beforehand, afterhand of like acid. So
Hmm.
you look at the acid, you look at the amount of hydrogens, right? If it has like in the first example, like if the oxygen is like four, it's gonna be like uh what were we saying like high sulf sulfuric acid, right? For this.
Hmm.
And then if it's going to undergo a reaction where it's losing its hydrogen, it's going to have one less. So it'll be sulfurate, right? Or like hydrogen sulfurate acid, right? Sulfate.
Hmm.
And if it goes again, then it'll be just sulfate.
Yeah.
Okay. Okay, cool. Let me know if you're running out of time. I think we went a little bit over, but
Um, we could do like one more.
okay. Ah, perfect. Math. Um,
Oh, and it's KSP stuff.
yeah, the irony.
Yeah.
Let me see, what did I do? So for this, I like showed my math. I knew that it's ultimately asking about what's the solubility. I looked at the units. I know it's asking in molarity, right? So it's moles over liters. And I knew that the KSP was given as 1.1 times 10 to the negative 10. Um, I think I just forgot like the formula off the top of my head. Like what is KSP equal to? Like the solubility constant.
Well, so let's not think in formulas. Let's do it from the ground up, right? So, first of all, we need to figure out what this reaction looks like, right? So they're giving us the barium sulfate,
Mhm.
and this needs to, well, I guess we need to figure out what does this turn into when
Mhm.
it dissociates.
So barium, um, and then barium, just wanted to look at, okay. So barium 2 plus, yeah, and then SO4 minus 2. Two.
So you could also just remember what we just looked at before with sulfuric acid
Mhm.
and how like the salt of that when it loses its proton is sulfate.
Mhm.
So here you can like what you just did is fine as well, but SO4 is going to be the 2 minus, so that could also help you with barium being 2 plus.
Okay.
So there's um they both have the same like coefficient, right? Like for 1-to-1 ratio of the number of bariums and the number of sulfates. So then this just can become the x, and this can become the x as well. And then your KSP, oh, and if you multiply these, you get x squared, right?
Mhm.
So then it's just your KSP that you set equal to the x squared, right? And so there's really just three variations of this. There's the x squared. Do you remember the other ones?
What are the other ones? It's like x times 2x or like
Yep, yep, yep. So it's even better if you don't remember it because then you can figure it out. So like if we just did the other thing where you have this squared and then you do this, you get what do you got?
you get 2x cubed.
Close?
Is it not 2x cubed? I'm sorry, 4x cubed because the 2 is also squared.
Good. And then this.
And this would also be like 9x to the fourth. Or no, I'm sorry, 27x to the fourth.
Yep. Good. So we have just the x squared version, and they're telling us 1 I'm just going to write 1e negative 10 equals x squared. Now, does it make sense that the square root of something can be obtained, is equal to taking it to the 1/2 power?
Yes, that I know, right?
Okay.
Because when you square it, right, like it's ultimately, yeah, like equivalent to x is, to the 1/2 power.
Mm-hmm.
Or yeah,
Square root, yep.
square root it, yeah.
So okay, so I'm gonna just bring this to the 1/2 power, this to the 1/2 power, which means we multiply the exponents.
Hmm.
So then this is 1e neg 5 equals x. All right.
Yeah, because ultimately you're just cross multiplying it, right? So 10 times 1/2. That's where you get the -5.
Yep, I don't know if it's cross multiplying.
Or like I guess you cancel it. Like if it's 10 over 1 times 1 over
Yeah,
2.
so I'm doing this to the power of 1/2, and if you take an exponent to the power of another exponent, you multiply them.
Hmm.
So 10 times 1/2 would give you the 1e negative 5.
And that would equal x.
Hmm.
Okay. Yeah.
What would you do if we had to do this?
Multiply. So 10 times 1 to the third power. So I guess it would just be like 10 over 3. Or if you wanted to make it into like a full number, like 3 times um 3 and 1 over 3, right?
Why don't we try making this divisible by 3?
But it would just be 10 over 3.
When I say that, when I say divisible, I mean can go into it cleanly.
Right. So it can go like 3 times, right? And you would give like 3, 1 over 3, right? So it's like does that make sense? Because 3 times 3 is 10.
So, all right. So what I'm going to do is
Uh-huh.
I'm going to try to make this divisible by 3. So I'm gonna do this. I'm gonna do uh left subtract, right add
Hmm.
to get this. And now 9 is divisible by 3, right? So I get 0.1. times 10 to the third power. And then I could just do left add, right subtract to get that.
So you're manipulating like the scientific notation of the one, right? So, um,
Yep. So it's divisible.
mhm. So you would move it to the left, yeah, and then you would subtract it. So zero point 0.1 e minus 9, and then it would make it easier for you to just multiply the 9 times 1/3. That would give you 3, and then ultimately you're just okay. I wouldn't have thought of that, to be honest. Just like manipulating the scientific notation with the one.
Yeah, I have ways of doing math that like a lot of people like. I remember spending like an entire like subway trip trying to figure out how to calculate the square root of a non-perfect square
Uh-huh.
without, using a calculator or anything. And I spent like a 45-minute ride thinking about it and I figured it out actually. But another thing we could have done is 100 times 10, left add, right subtract to the power of negative 12. And then
Mhm.
that 12 is divisible by 3 as well.
And
So,
then you it would give you like 100 e to the -4, and then you just kind of fix your scientific notation
yep.
accordingly. Yeah, some people just scroll on TikTok for 45 minutes, but some of us are, you know,
Yeah, I literally am always thinking about photons, positrons,
yeah,
um, things like that. KSP.
of course, of
But
course. And then day trading in the day, right? Kind
yes,
of
yes, yes,
balance it
yeah.
out.